Okay, greetings all. Today we're going to be talking about Fibonacci and Lucas identities. This will be part 3, maybe the final part of the series. We'll see how that goes. But where we picked up from where we left off in the last video, again, we were showing where we had run into some of these Fibonacci and Lucas numbers in our study of Bamidbar, right? The book of numbers, the biblical book of numbers. Excuse me. And we were looking at our synthesis and finding some of these ties. What I hadn't, I meant to touch on that last video was some of this that you find in the finding of Levi. When you find this number of 2250, this number is interesting in a number of ways. I think one of the connections was the 273, the moon sidereal numbers, which you find when you find the relationship of the eagle grouping minus the man grouping, and you divide it by this number, you end up with 2.73 repeating. And you run into this number again here in the this Manasseh North bifurcation, the second census. But you also find it right here if you subtract. Again, you had the Pekod singling out Issachar, Zebulun, and Reuben together in the, if you look at the Hebrew of the second census in that scripture. And this 90-degree piece here, you see that we've got this remainder that ends up being the 6850 that we can reduce down to 137. Again, fine structure constant. We saw the 4.07 relationship to the 4070 of Levi. So this is an oat, right? That's an aleph, vav, and a tav. So the end and the beginning together. Okay, so this a sign that means a sign. But at any rate, the difference there. This so if you take 6850 and subtract this 2250, again you end up with that 4600. Again, pointing to that moon sidereal. But how else is this interesting? Well, this number right here, this degree, if we're going to look at this in the degree, the number that we get, the 13370, again, we had noted in our tables, which we're going to go look at, those clean tables of the 20 to 1. And again, recall that our addition here of Levi and the bifurcation of Reuben right here, this is going to be 4070 plus 4080, that's 8150. Okay, so we'll see 8150 when we combine these. We subtract these over here, we get 4600. Well, that table that we had, that clean table, again, 21 is where we got pointed down this ratio of this 13.36, which we showed was the sort of the relationship between the moon sidereal and the sun sidereal. So it's sort of the ratio between those, and then we find that numerical value, when we put it back into 40,000 or the 605,800 to find that number, it was 4,600. And so anyway, we'll go back over here. I know I'm rambling here, but yeah, in that table we saw that 8150, right? So this sequence also produces an 8150 right here, which is kind of interesting that shows up in there. But we're looking at this degree. I meant to show you this. So we were thinking of all of the different ways we can extract some meaning out of some of these given numbers that we're given here. Well, this 2250, we get this degree pattern. If we come over to our sequence, our sequence finder right here, we can try a couple things in here. So one other thing I meant to show you on this, that quarter of Israel, the 151,450, was when we ran this in, we plugged this number in, and this right here is going to calculate, divide this by 5, and then run it all the way back. We find our next number here is 93,601, so we can round this off to a clean number, put 93,601 in here. This will subtract it evenly back, and we see when we pass 0, it's 273, 233. So that's one thing that we noted in here on this grouping of man, is these are numbers. This is the number that we see relative to this. It's 233 times 13 is at 3029, 3029 by that least common multiple of 50 that all these numbers share gets you to 151, 450. So it's interesting that you find that number there, and then when you run this in your sequence finder, your starting interval is 273, and of course there's a whole chapter dedicated to 273 basically in this book of numbers. So, and that's relative to the moon sidereal again. So what were we going to show? Okay, so we were going to look at, in this block right here, we're just going to punch in 2250, and we're going to divide that by 605,800 to get our percentage of the whole. And then we're going to multiply that by 360 to get our degree representation. And that's going to come out to this number, this 1.3370. Again, that's relative to that 20 to 1 constant that we found in that first chart. So when we actually run this through and then find the number next to it, and we're going to run this through and find the multiples of this. So this is going to be descending by phi, and this will be ascending by phi, going down this way. Well, we run into a couple numbers here that are kind of interesting to us. So one of these, so this will be phi to the, once we get to the 8th power down here, we'll notice that we hit on this 628 and 1644. So these are a couple of interesting numbers. So we know that pi is going to be this number here, 3.1415. And we also use 22/7. Ptolemy, when he, we're talking 180, this is before trigonometry, that we have modern trigonometry, but he used a 120 arbitrary diameter for a circle. And then he found that the circumference would have ended up 377, which we recognize now as this is our 14th Fibonacci number. So if we were to divide 377 by 120, we would get that phi number that he would find as well. But where was I going with this? Oh yeah, so 628. We find this pattern in the numbers right here. So we know that pi just gets us halfway around the circle. So we multiply this by 2. This will be essentially our distance around the circle. And then we're going to multiply this by 10 just to kind of see how far we're off. And we're going to take this and we're going to subtract it by this figure we find here. We find that we're pretty close, right? We end up being 178 thousandths off, and I think there was something with 178. Yeah, so 178 divided by 2 is 89. So again, that's another Fibonacci number that we find there in that pattern of numbers. But it's kind of interesting that you're 178 ten-thousandths off when you're finding the difference between that. But if we look at phi squared, if we're going to go 2 spots down, so we're multiplying this by phi squared, we're going to end up with this pattern of numbers, 164.44. This might not catch a lot of people's eye, but it did me, because I know that if we're going to look at our number for phi here, we're going to square that. We're going to come up with this number, 9.869. Again, this is another pattern of numbers. It's relative to our Fibonacci number here of 987, right? So it's kind of, this has been, people have noted this before, obviously, but I'm not sure. So when we divide this number by 6, this is going to be our formula for our constant for the zeta function, the Riemann zeta function. So when we're looking at this it ends up being pi squared over 6. But if we look at what this is trying to show us, this has to do, again, with what Ptolemy is talking about with epicycles, and he's trying to track the planetary motions and everything. But you're getting into sort of this type pattern would be a graph of this function. But yeah, you end up getting into sort of these, sort of like a Mandelbrot type deal here, with the way this thing, kind of these cardioid patterns with this function. So it's interesting that shows up in here. So I wanted to point that out, because, you know, how far are we off with this pattern here? So if we take this, and again, we're going to take and we're going to multiply this by 100. We're going to get this number, and then we're going to look and see how far off we are from, we'll take this number, subtract our number that we found here, and we're 44 thousandths off. So pretty interesting that you hit on a couple of those things when you punch this degree finding in here. So just wanted to show everyone that. And continuing on our Fibonacci. So I'm finding these tables. I start building some of these tables, and I'm kind of looking at some of these constants, but it's not quite right. Some of these constants. So one of the things I find doing these groupings is the relationship between Fibonacci and Lucas. So if we took the Lucas sequence here, and we're going to build a Fibonacci sequence, and we're going to add these together, we'll create a sequence here. And then what we see is if we take this sequence and when we copy it, and then we drop 2 positions down, we're going to paste the values here, and then we're going to add this across. We're going to add these together, and what we end up getting is we end up getting the Lucas sequence here. So if we take and we're going to continue this up here until we get past 0. So we have the Lucas sequence. So we see how this sequence, we drop it down 2 positions, add it across, and we get the Lucas sequence. Well, what I started going through is I just started to look at, okay, well, what if we started with the Lucas sequence, and then we took this and we dropped this down and then pasted these values in. And then you end up, basically what you see is you loop back to, you end up with this sequence, which we can see is going to end up being our base Fibonacci sequence times 5. And that would make sense, because this is the base Fibonacci sequence times the square root of 5 gets us to Lucas. Lucas times the square root of 5 gets us back to the Fibonacci sequence times 5. So we're just sort of looping through. So, you know, I started looking at, okay, when we do it with the Levi sequence, that's what I call it. You know, it's the same thing. We loop back into an 11-8. And so on and so forth. An 11-8 into a 25-5. So I started looking at, okay, if we tried a 5-2, because when we looked at some of these sequences over here, for instance, like a, you know, whether we wanted to look at a 273, 233, or even if we wanted to look at the total of a 2116, some of these other sequences, just to kind of see what would pop out. You know, I decided to see if there's some sort of relationship. So I went through all this headache and all this trouble of trying to find how these things work together. Like, is there some sort of formula that you can come with to build a table? And that's exactly what I ended up doing. And I ended up building this type thing right here. So what we have here is let's expand this out. So I come up with this formula. So you end up with, there's two different, you got to break this up into conditionals, because your formula is going to be different as soon as you get past the halfway point of your relationship here. So for instance, this top formula works for the Lucas sequence. The bottom sequence works for the Fibonacci order. And what this does is this is going to align you so that your constant that this produces will be the constant that when you multiply this by phi continually will generate this will be the harmonic for this kind of ideal sequence that you have. So you're going to be just below, just above, just below, just above, just below, just above. So you're kind of buzzing around this sequence. So we know that working with clean numbers, we generate this Fibonacci sequence right here. But this can be generated from this base number right here, which ends up being, obviously, I mean, if we could take the square root of 5 and add 5 and then divide it by 10, and you see that that's the same pattern of numbers right there. So, and I've got some other ties in here because these two should be a difference by the square root of 5, but when you divide these across, they end up being a slightly different relationship. So this 2, 1 will produce a 5, 5. So if we were to produce a 5, 5 in here, you'll see that this will generate our sequence, and then we're off by, ends up being the square root of 5 times phi. So you'd almost have to go a step back from where you're starting to produce this sequence. You got to go a step back, divide this by phi to kind of get the relationship that really should be. And that ends up being this formula right here. So this sort of, if you go a step back, this would be your start point to produce your interval right here. So just depends on where you think that this should start, but at any rate, this ends up being the formula that I came up with for this, that will produce these sequences for you. So again, if your interval is greater than 2 times, greater than or equal to 2 times the start, you would use this first sequence right here, and then if it's less than 2 times the start, then you would use this over here. So again, 5 to 1, we would use this sequence right here. This is our Levi sequence, the 5 to 1, and it produces, this is going to be different than that other chart when I was comparing this to the base. So like I said, this is sort of what I arrived to. So again, a 5 to 1, this will be the constant, this would be the formula. So it's your interval, which is 5, times this value, which is the square root of 5 minus 1, which is right here, plus 2 times whatever your start is, which is 1 right here, divided by 2 times the square root of 5 gives you this constant right here. And this constant, when you plug this in right here and multiply it times the square root of 5, you see how it's going to harmonize. It's going to become this sequence. Again, it's above, below, just like you have to do with the Lucas sequence with your correction right here. So you got to basically take phi, and you got to take the descending pattern of phi, and then you got to add and subtract it to get to your pure number. So it's the same thing right here. And so, and then what you have here is going to be your second interval ends up being from your first. So this is going to generate your other pattern, which will be the square root of 5 times this pattern will generate your other pattern. So this is part of your loop. So if we looped over here from 11, 8, this is going to loop us back to a 25, 5, which is 5 times our base figure right here. So it just loops you back. So what you get for the formula of that is going to be your second interval ends up being here. It's 2 times your base interval plus your start on the first interval. And then your start ends up being your base interval here plus 3 times your start gives you, and you see how that comes out. And for whatever reason, it comes out like this in every situation. So as long as, like I said, a 5-2 is going to produce a 12-11, and then when we punch 12-11 down here on the other side, it'll loop back to a 25-10. Now you can get, this will look like it works here if you do like a 5-3 right here. If you do a 5-3, it'll generate a 13-14 pattern, and then 13-14 will generate a 25-15, which that all looks like it's right. But again, you got to remember that you're trying to find the interval, that starting interval, and this isn't really your starting interval. I mean, I guess it can kind of be, but you can go further back. So this would be a 1-13. And then from your 13-1, that would be a 12-1. So you see how you got, it's not going all the way back. So really you'd need to put a 5-3 in over here. And that generates your 12-1. And then you can put your 12-1 in over here and see how it loops back to a 25-15. But at any rate, yeah, I built this tool just to kind of check out and see kind of how this all works. And I thought that was pretty neat. So I went through all of this kind of the rigors of messing around with this. But you know, I kept seeing some of these numbers pop up in here, sort of like right here with this. I kept seeing this tail on this number. So where the heck was that? I just saw it. 2-1 to a 5-5. But anyway, I saw that it's basically going to be this number right here. Okay, so it's in our base Fibonacci. That's what it is. So our base Fibonacci, I kept seeing this number right here. And so the square root of 5, remember, is interesting because, you know, we're dealing with a 360-degree circle. And then we know that if we divide this up by 5, we end up with 72 degrees for each piece of the circle. So we divide this into a pentagram, I guess. 72 degrees per, but you know, the square root of 5 is kind of what we're dealing with here. So if we know that 72 times 5 is 360, well, the midway point is going to be 72 times the square root of 5, which puts us right at 161. And we see that if we were to add 161 plus 72, we get back into this 233 again, which is that's that Fibonacci number that kind of calls our attention. But so this 161 ends up being kind of interesting. 161 and 233. 161 happens to be, if we were to multiply 161 times itself, we get this number 25,921, which when we're looking at 25,920 is going to be that number that everybody's going to associate with the precession of the equinox. And if we divide this by 72, we get 360 degrees. So it's 1 degree every 72 years is what they calculate for the precession of the the sun coming around. The difference between the tropical and sidereal solar year, the sun basically advances on the background stars. It's going to take you 365.2 whatever it is days to complete your year, but it's off by like 20 minutes. So there's 40 minutes in a day. You divide that by 20, and it's going to get you to 72 years for you to be off that basically 1 day. So 1 day. And it's interesting, that the sun, when we're looking at the sun and the moon and the stars and the cycles of those things, that they're both traveling the same direction. So the sun would be traveling the same direction as the stars, but you see that the sun's only advancing on the stars by about a degree per day, a little bit less than a degree. So it takes a full 365.2 revolutions of the sun for it to hit in the same spot in the background stars. So that would make the background stars, it would mean that they've made, taken 364.2 laps or whatever to get to that point. And then the relationship of the moon to the stars. So it's the moon is, we're going to count 27.3 days for the moon to make its way all the way around and hit the same position in the background star. So when we're looking at the sidereal of the moon to stars, it's important to keep in mind this 365 to 364 to 27 relationship, because this is also a right triangle. So if we were to look at 27 times 27, 729, and we know that this is equal to 365 plus the 364, and that's a primitive right triangle there. So this relationship, it's all geometric, and how exactly it works, who knows. But there's definitely a interesting thing happening here, because obviously 40 minutes in a day, and the moon's falling back on the sun by 52 minutes per day. I forget where I was going with this, but at any rate, that's going to be a whole nother video that we can do. But where was I going down the path of this? Okay, the square root of 5, and okay, so we need to do. This got me down kind of a study of a pentagon and the breakup, the geometry of a pentagon. So we'll take this and we'll get this out of here for a second. We'll take a look at tables. What are we talking about? Okay. Sheet 5. Okay, so I got to looking at this. So again, we're dealing with phi, and it's got to do with the breakup of a circle and a pentagon and a pentagram here. So again, this is going to be interesting. You need to look at Andrew Hoy's work, Project 314, because his tabernacle, this is basically a 10. It's going to be a 10-sided polygon is going to be the breakup of the construct. So again, we're working from this other train of thought of this base design in the center of all of this. But just to look again at the geometric breakup of this pentagram, again, this would be a pentagon with a regular pentagon with a side of 1. And we know that the diagonal, all the diagonals of this is going to be equal to phi. So now you're going to do up the breakup. I forget what they call this. Apothem, I think they call this, is the distance between the side to the center. And I forget what they call it. Maybe it's the radius of the circle that's inscribed here is going to be from the center to the point. So that would be the radius of the circle that circumscribes this thing. And then they call this the apothem from the center to the short side of this side. So anyway, the breakup ends up being, because we know that this is phi, the diagonal is phi. We end up taking 1/2 of the side, and we square this to get 0.25, and we subtract this from phi squared, which we know is 2.618. And you end up with this figure right here, 2.368. You take the square root of this to get 1.5388, and that's going to be the height of this thing. So the height, though, if you divide this by the square root of 5, you get that's the ratio of the height of the apothem. I haven't seen anybody mention this as far as the relationship between these things. You see this big formula to find this apothem, but basically if you just take the height right here, and you divide it by, if you divide this by the square root of 5, you'll get this figure right here. Pretty sure anyway. Make sure that I'm not telling you lies here. Where is our square root of 5? Okay. Yeah. Yeah, 0.668. Yeah, so that's what it is. So I haven't seen many people mention or anybody mention that really, but that's something that I had noted. And then, so yeah, that's the relationship there is the square root of 5, and then the relationship to, yeah, basically what I did was, you know, once you break this up, these are going to be all the lengths of all of these things, and then you get a smaller pentagon in here, and the length of that side is going to be this number again, this tail, and it's you do find this again with the ratio of that 233 and 161. So I think if you look at the ratio of 233 divided by 161, yeah, that's that number again, that 14472. So you see that same sort of tail that's happening there, and it's one off. So you do see this quite a bit, and so it got me thinking about sort of the breakup of this thing. And then I was thinking about the angle. So the angle of this would end up being, you know, we know that if we're just thinking of this is flat to the ground, we've got a 90-degree piece coming up here. So how far off of 90 are we carrying this over? Well, this would be 18 degrees indexed over to the point here. So off of straight up, we're going to rotate this over 18 degrees to hit our point. And then from here, we're just going to keep adding 72 degrees to rotate this around. 72 degrees to rotate to the next, and then 72 to rotate to the next to see what our what do you call it? Our rotation right here is. So from 18 and then to 90 and then to 234 to 306. So it got me thinking of seeing some of these numbers. So we know that we're adding 72, and this is going to be all of our multiples of 72 here all the way through. And this produces numbers that we've seen in here. We've seen 432 in the 288. We've seen some of these numbers pop up pretty continually in these biblical numbers that we're looking at. But I thought, like, if we're starting 18 degrees and then we rotate to 90, and then we rotate another 72 to 162 and 234, well, I've noted that I've been seeing 233 and I've been seeing 161, and I know 89 is a Fibonacci number. So you just I subtracted one off of all of these numbers, and I create a whole series of numbers right here. Well, you know, there's a bunch of stuff that pops up in here. So when you do this, and remember that, like, all of these calendars that we're dealing with, whether we're dealing with like a 90, like if we're talking about breaking up a circle into 360 degrees, and we have 90, and then we've got 180, and we've got 27 and 36. Yeah, it would be 180. I'm all over the place. 180, 270, and 360. You know, the calendar, like the 364 calendar, you got to add in that day, sort of like adding in that harmonic day. So you're adding one in to get to 91, and then 182, and that's Jacob, right? Jacob. 273 would be the third day, and then 364. And then we know with the Gregorian calendar, you're adding that one day in. Well, for 365, you're going to add the 1 day in for 365. So you would add that one, and then every fourth year on the Gregorian, you're going to add another in to get you to 365.25. And then actually you got to take 1 day off every 100 years. So it takes you down to 365.245. And then you know that pattern repeats every 400 years. So Gregorian times 400 gets you to this many days. And so you know that 364, if you were to look at how many days difference you are on a regular 364 calendar, you end up with this difference, which ends up being this number minus this number. Oh, this is not right. 365.2425. Okay, 497 ends up being your difference. And of course, that's the difference is 71 weeks. Divide that by 71. So, oops. Divided by 71. And so, oh yeah, okay. Divided by 7, I'm sorry. So we get 71 weeks. Now we know that a 364 is going to be 52 weeks. And so the difference is 19 weeks. 19 weeks over a period of 400 years. Well, it's interesting. You run into this again with the 168. I'll get to that in a second, I guess. But at any rate, I'm jumping ahead of myself. So I'm looking at this 18, I'm subtracting the 1, and I run this down and I find all of these interesting numbers. So obviously 45, all of this number for Levi, obviously that's going to be there, 45 and 2250. But you also hit on this 449 number. So again, 449 is going to be, we run into 449 times 44, ends up with this figure here, which we see is going to be that eclipse cycle times 3. So a third eclipse is that many days. And that has the factors of 44 and 449. So that shows up right here. And also like 593, that's Simeon's number. 733, these are all numbers that we find in when we look at the actual breakdown of the censuses. But one thing that you do find with this, you're going to see 233, 377, 521, 665, 809, 953, 1097, every other number in here. I've seen these numbers, and where you see it is going to be in this table right here. Right here, when you're looking at the 13th order of this, it's going to be 233, 377, 521, 665, 809, 953, 1097, so on and so forth. So you're going to see that pattern of numbers all through here, which is pretty interesting that happens. That you hit on all of those numbers as you're going through that 13th order. So that pops up. And then when you raise these up by 50, you can start to see some of the numbers that you hit that are in our censuses. So obviously 810 is a number that we hit. That's going to be both Ephraim's number in the first census and Gad's number in the second census. So that pops up there. 153 is a number that shows up here. This is going to be relative to Judah in the second census, actually. And we'll see this later on as well. It's 76,500. So this ends up as a multiple later on here. So that shows up. It's just kind of interesting, some of these things. 737 again, when we look at if we're going to look at the censuses, census 1, 737 was bifurcation of Asher right here in the second census. So that shows up. Again, Judah's number is 76,500, 1530. That's going to show up in that series of numbers. Just kind of interesting. Some of these things that pop up. 40,500 is a number that shows up in there. So it's just something that I noted today when I was looking at this. That it just kind of popped up on there. So all of that's pretty fascinating. Again, I wanted to know where this might cross with the 605,800. So I come all the way down to 605,800 to see where it crosses, and we're off by 100, but it hits right at 168. So when you look at, I looked at the descending order as well. So what I did was I looked at another series. Instead of going 18 this way, I looked 18 the opposite direction. So basically hitting on 342 and basically looking from this other direction and looking at it every 72. And you hit on some interesting numbers in here, 199, 271, are numbers that are kind of interesting that you run into, but not nearly as many as you hit on this other, go in this other direction. It's pretty interesting, some of these different numbers that you run into. But this order right here going the other way, when you hit at 168, again, you hit on 605, 800, pretty close to that, and then the 603, 550. You kind of miss by 400, 350 to 400 on this side, and you miss by 100 over here. So that's pretty interesting, and it happens at 168. And again, 168 is going to be that ends up being the addition of, in your census over here, when you get given these numbers and you boil them down, the difference between the man grouping and the eagle grouping is 123. Again, that's going to be the number, this 123 number that you get right here, 6150. This is going to be the start of how you get that sidereal. This is how I found the moon sidereal, because when you divide that by your Levi number of 45, that comes out to 2.73. And 373 again is going to be a number that you find in Judah. So when you're looking at 74,600, and you're going to find that's the largest factor of Judah's number is 373. So that pops up in there too. 1365 again is that shekel counts, 273. You got to multiply it. They tell you to multiply it by 5. It'd be helpful if I made this an equation. So 1365 again. So all of that kind of shows up. But just to show you, we were looking at that. We're looking at the Gregorian compared to a 364 calendar, and you do see this relationship in there. So the relationship between these numbers, 71 weeks to a 52, the difference of 19. It's essentially the same ratio of this 168 to 123 to 45 ratio that you're getting right here. So you're seeing that all of these are going to be this number divided by this number, and they're all this 2.36 whatever number. You can average this out. The sum of those three is 7.1. We can divide this by 3 to find the average. Yeah, 2.36 repeating here. What's that telling us? I don't know, but it seems relevant that again, right here we're looking at some of these different relationships. So 168 to 123 as 71 to 52. So we're looking at comparing the ratios to all these things. So interesting that happens at 168. Another thing with 168, obviously it's the multiple of two perfect numbers. So if we were to take 28 times 6, that's 168. 28 and 6, I think, are when you're looking at, again, with the recreational mathematics, these are the first two perfect numbers. So it's they equal the sum of all of their factors, I think. So it's kind of an interesting thing that happens. So that happens. That pops up in there. So it's kind of, again, that's pretty interesting that this just sort of happens when you're looking at this geometry like this. So one last thing I wanted to touch on in here was there was this, I had found this guy right here. This guy had put this video up, and he talks, I think he mentions in here that he's kind of running in the same problem that most people have is, you find all these things, and I've reached out to universities and to pastors and to rabbis I've reached out to so many people to try and show some of these things to, and most people are just kind of, they just don't want to hear it. It's sort of like they're kind of already set in their beliefs and their understandings and stuff, and they're not open to seeing anything new. And this guy had found this relationship of Lucas to Fibonacci that I had found. And basically he's taken these squares and sort of how you build your Fibonacci squares out here. He found that the center of these, there's a relationship here that relates to the Lucas sequence. And so the distance between these are all relative to a Lucas number times the square root of 0.1 is what he had found. So what I did was, and everybody should go check out, he's only got 336 views on this thing, but it's a pretty interesting find. I don't think I've found any other, in those identities, I hadn't found anybody that had found this thing, so I'm sure people have experimented and found a bunch of stuff in here. But yeah, check out this video. And then over here we've got, I'm trying to think where I found so this is the squares, but on sheet 4. So I kind of did the same thing just to see, because I tried to spiral it out and then spiral it back in. So I thought if I could build this spiraling out this way, so I could spiral out, and it's hard to get these squares exactly square, because then it ends up looking all weird like this. But basically you spiral out and you get to a point where it's like, okay, now you want to maybe spiral it back in. So I can't remember where the point that I hit where you spiral back in. It must have been up here. So spiraling out, and you hit, and then you start spiraling back in, and you kind of spiral back in over on this side. So I kind of was playing around with that to kind of see if there was some kind of cool thing with some kind of Mandelbrot or Riemann type thing. But then I found, I decided to break down the actual, the breakup of this original square. So basically what you get is, you create that first square, and the center of this is going to be off center of the first block, and you end up with this sort of indexed view of one to the other. So the Fibonacci squares are all going to be this even 90, and then you're going to be sort of it's all going to be indexed off this degree, and this ends up being a 3. You can see how this becomes a 3 to 1 right triangle. So this would be 1, and this would, the third block up right here is where that would come to a point. So you end up with a 3 to 1. So you get a 1 to 3 to the square root of 10 would be the relationship on this right triangle. The hypotenuse would be the square root of 10. So anyway, with that in mind, you can start figuring out, like, if you base this off of a size 1, if this block is 1, then you get the breakdown of this ends up with all of these crazy numbers. The square root of 8/45, the square root of 1/90. So what I did was I tried to find a way that, like, the base of this would be something that would be easy to see with a square root of 10 or something. So what I did was I ended up finding, if you arbitrarily set the dimension of this square 30, then you can see that the breakdowns make it, by thirds. So it's going to be, you'll have a 1 to 2 relationship, and then this will be like a 1/6 of 30, so that's a 5. So then your smallest element ends up being the square root of 10, which is this little segment right here. It's interesting how you find all of these different pieces to this, and but yeah, you're just going to take this origin block, and this origin block will have these two axes, but basically as you grow from this block to the next, you're not going to use this second axis anymore. It'll just be this block with this sort of red or this purple split, and this is split to like 1 to 2. It's always 1 to 2 on this, but you just rotate it around and grow it out. Rotate it and grow it, rotate it and grow it, and then you'll see how this you'll create this big cross in here. So this cross is off center. This is going to be the breakdown of how far that's off center, though, and all of the different dimensions. So it would need what this ends up being 4 root 10, and then you see how when you rotate this out to get to the center, you're gonna take a 5 root 10. So it would take, you would see how when you rotate this up, this would be touching right here, and to get to the center you would need 5 plus 4, and then the next one over would be twice the size. So you would have this 2 plus, you'd need a full 10 to get to the middle, which would give you 12. So you end up with this, once you add this out, it's 3, 9, 12, 21, and you find that it's the Lucas sequence times 3 is what you end up here. So you can boil this down to the Lucas sequence times the square root of 10, so that's all proven out and stuff. So I checked that out just to double check and to actually give an actual breakdown of this, and sure enough, that's what you get. So it's pretty interesting. You find everything, I think, except for 9 root 10 and 7 root 10, I think, in here. So every other dimension you find in this base block. So anyway, I just thought I would share that because that's another thing that I stumbled upon, and I think that's going to do it for the Fibonacci stuff, Fibonacci and Lucas stuff. It's definitely, they're connected. It's back in these numbers from these tables. It's just crazy how it's you know, like I said, just finding this one piece gets me down and finding all of these different things about the relationships of these numbers in mathematics and stuff. So yeah, hopefully someone out there will want to see this and want to maybe get involved and try to understand the breakup of this and kind of see where it's going, because there's a lot of things I think to be drawn out in this. But hope you enjoyed that, and we'll see you on the next one, I guess.